Dear students, welcome to the lecture on representative elements. In the periodic table, the S and P block elements are collectively called the representative elements. In the present module, we will discuss about the elements in group 15, 16, 17 and 18. That is the nitrogen family, oxygen family, halogen family and the inert gases. The elements in the nitrogen family are nitrogen, phosphorus, arsenic, antimony, bismuth and moscovium. The elements of group 15 or nitrogen family are also known as pnictogens. The name is derived from a Greek word which means to choke. This refers to the choking property of nitrogen gas in the absence of oxygen. Nitrogen and phosphorus are nonmetals. Arsenic and antimony are metalloids. Bismuth is a metal and moscovium is a highly radioactive synthetic element. The electronic configuration of the elements in nitrogen family is Ns2Np3. For nitrogen, the atomic number is 7. The electronic configuration can be written as helium plus 2s2 2p3. That is 1s2 2s2 2p3. Phosphorus has the electronic configuration of neon plus 3s2 3p3 and so on. The outermost electronic configuration of bismuth is 6s2 6p3. So for all the elements in group 15, there are 5 electrons in the outermost shell. For arsenic and antimony, the electrons are filled in the d orbitals, n-1 d orbitals. Thus the electronic configuration of arsenic is argon plus 3d10 4s2 4p3. That of antimony is krypton plus 4d10 5s2 5p3. For bismuth, the penultimate d orbital is filled as well as the anti-penultimate f orbital is also filled. Thus the electronic configuration is xenon plus 4f14 plus 5d10 6s2 6p3. As we move down the group, the atomic size increases. The atomic radius of nitrogen is 70 picometer, that of phosphorus is 110 picometer, and this increases up to 148 picometer for bismuth. We can note a pronounced increase from nitrogen to phosphorus and from phosphorus to arsenic, antimony and bismuth. There is an increase in atomic radius, but it is not pronounced as in the case of nitrogen to phosphorus. This can be explained on the basis of shielding effect of electrons. In the case of phosphorus, there is a strong shielding effect by N-1 s and p electrons. Whereas in the case of arsenic and antimony, the N-1 d electrons show poor shielding effect, and in the case of bismuth, N-2 f electrons and N-1 d electrons also show poor shielding effect. As a result, the increased nuclear charge is felt more on the outer electrons of arsenic, antimony and bismuth. As the effective nuclear charge is more felt on these electrons, the electrons are pulled more towards the nucleus and thus there is no pronounced increase in the atomic radius. If we observe the ionization energy, it decreases as we move down the group. Among group 15 elements, nitrogen shows the highest ionization value of 1403 kilojoules per mole, and bismuth shows the least value 703 kilojoules per mole. Ionization energy is defined as the energy required to remove the most loosely bound electron from an isolated gaseous atom. So as we move down the group, as the atomic size increases, it is more easy to remove the loosely bound electron. Thus, the ionization energy decreases down the group. And if we observe the decrease in ionization energy values, there is a sharp decrease from nitrogen to phosphorus, and afterwards, even though there is a decrease, it is not as pronounced as in the case of nitrogen to phosphorus. This can also be explained in the terms of poor shielding effect of the F and D electrons in the case of bismuth and the D electrons in the case of arsenic and antimony. As we move down the group, the metallic character increases. Nitrogen and phosphorus are non-metals, arsenic and antimony are metalloids, and bismuth is a metal. As we move down the group, the ionization energy decreases and hence the metallic character increases. The electronegativity of group 15 elements decreases as we move down the group. Nitrogen shows the highest electronegativity of 3.0. For phosphorus it is 2.1. Afterwards, in the case of arsenic, antimony and bismuth, the decrease is not much pronounced. This is also regarded as a consequence of the poor shielding effect of N-1 d electrons in the case of arsenic and antimony, and N-1 d electrons and N-2 f electrons in the case of bismuth. So the electronegativity values of arsenic, antimony and bismuth are very close to each other. The elements of group 15 shows generally -3, +3 and +5 oxidation states. The tendency to exhibit -3 oxidation state decreases as we move down the group. This is due to increase in size of the atom and increase in metallic character as we move down the group. Thus, nitrogen has the highest tendency to show an oxidation state of -3. Due to inert pair effect, the stability of +5 oxidation state decreases as we move down the group, and the tendency to show +3 oxidation state increases as we move down the group. Thus, nitrogen has the highest tendency to show +5 oxidation state, whereas bismuth has the highest tendency to show +3 oxidation state. Due to the poor shielding effect of D and F electrons, the effective nuclear charge on the outermost S electrons acts strongly. That is, the nucleus will pull the S electrons more strongly, and consequently the two S electrons will show a less tendency to participate in chemical reactions. This effect, which explains the reluctance of S electrons in the valence shell to participate in chemical bonding, is called inert pair effect. An example for inert pair effect is bismuth has a tendency to exist in +3 oxidation state compared to +5. It has 5 electrons in the outermost shell, 2 s electrons and 3 p electrons. Due to inert pair effect, the s electrons show reluctance to participate in bonding. Thus, the p electrons are more involved in bonding, and bismuth always show a tendency to exist in +3 oxidation state. Because of this, bismuth 5 has a strong tendency to reduce to bismuth 3, and thus bismuth 5 is a good oxidizing agent. Nitrogen shows various oxidation states from +5 to -3. When combined with an electronegative element, it shows positive oxidation states, and when nitrogen is combined with an electropositive element, it shows negative oxidation states. For example, in nitrogen oxides, nitrogen shows plus positive oxidation states. In NO2, the oxidation state of nitrogen is +4. When combined with an electropositive element like hydrogen, the oxidation state of nitrogen is negative. In NH3, the oxidation state of nitrogen is -3. In NH2OH, the oxidation state of nitrogen is -1. A reaction in which the same species is simultaneously oxidized as well as reduced is called disproportionation reaction. The compounds of nitrogen undergo such reactions. For example, HNO2 decomposes to HNO3, NO, and H2O. In this example, nitrogen is oxidized as well as reduced. Thus, the reaction is an example for disproportionation reaction. In HNO2, the oxidation state of nitrogen is +3. In HNO3, it is oxidized to +5. +3 is oxidized to +5. In NO molecule, the oxidation state of nitrogen is +2. Here, the +3 oxidation state of nitrogen is reduced to +2. Similarly, the compounds of phosphorus also show disproportionation reaction. H3PO3 decomposes to PH3 and H3PO4. +3 oxidation state of phosphorus is changed to -3 in PH3, and H3PO4 phosphorus shows an oxidation state of +5. Thus, +3 is reduced to -3 for PH3, and +3 is oxidized to +5 for H3PO4. Coming to covalency, the maximum covalency of nitrogen is 4, and all other elements of group 15 show a covalency greater than 4. This is because nitrogen has only 4 orbitals, that is 1 s orbital and 3 p orbitals, and it cannot expand its valency beyond that due to the absence of d orbitals. And for the same reason, the compound NCl5 cannot exist, whereas the pentahalides of other elements of group 15 exist. Comparing the physical state of group 15 elements, nitrogen is a diatomic gas, and all other elements of the family are solids at room temperature. And nitrogen and phosphorus are nonmetals, arsenic and antimony are metalloids, and bismuth is a metal. As we move down the group, the density of the element increases. In the case of nitrogen, the N2 molecule is formed by triple bond. That is, one sigma bond and two pi bonds. The hybridization of nitrogen in N2 molecule is sp. The sp hybridized orbital, one of the sp hybridized orbital of each nitrogen forms the sigma bond and other sp hybridized orbital contains the lone pair. There is p-pi bonding between the unhybridized p orbitals of each nitrogen and two pi bonds are formed. The nitrogen-nitrogen bond has the highest bond energy, that is 945 kilojoules per mole among all the homonuclear diatomic molecules. N2 is highly stable and less reactive. All other elements of group 15 are solids under normal conditions. Like nitrogen, phosphorus also forms pp triple bond, but the pi bonds formed by phosphorus are very weak because the effective overlap is not possible. Overlap of p orbitals is not possible in the case of phosphorus as compared to nitrogen. The occurrence of an element in more than one physical shape is called allotropy. The diverse physical types of similar elements are called allotropes. They have different physical properties but comparable chemical properties. The elements of group 15 show allotropy. Nitrogen exists in alpha and beta forms at very low temperatures. Phosphorus exists in 4 different forms: white phosphorus, red phosphorus, black and violet phosphorus. Arsenic also exists in 3 different forms and antimony in 2 different forms. The various allotropes of phosphorus are shown here: white phosphorus, black phosphorus, red phosphorus and violet phosphorus. White phosphorus exists as P4 tetrahedra. Red phosphorus is formed by heating white phosphorus at about 300 degrees Celsius in the absence of air. The red phosphorus exists as an amorphous network. Black phosphorus is the most stable form of phosphorus. The allotropes of arsenic are grey arsenic, yellow arsenic and black arsenic.